Today we're going to look at similar solids, and we'll also look at congruent solids, and you can see that a little more in the objectives. So looking at congruent and similar solids, and to look at some properties of some congruent solids. So we've talked about similar figures before. We spent a whole lot of time on similar triangles, and then we spent a whole chapter on similar figures as well. So this is kind of an extension of those sections. So as you can see, what we already know about similarity. They're going to be the same shape, but not necessarily the same size. Just like you can look at the similar triangles or the other similar figures that we've dealt with by looking at their linear measurements. Again, the corresponding sides have to be proportional, things like that. Two polyhedra, that's the plural of polyhedron, which is again just our 3D shape. I'm looking at two similar 3D shapes. All the corresponding faces, they must be similar, and all the corresponding edges must be proportional. So it's kind of just an extension. Like I said, we have all the properties and rules that we went through with similar figures, and now we're just applying it to the 3D shapes. So let's look at these first couple examples. Here's two rectangular prisms. So I'm looking at these and determining if these are going to be similar. So according to what that last slide said, all the faces must be similar and all the edges must be proportional. So we're going to look at that second one and spend a little more time with that second kind of characteristic with the edges being proportional. So I'm going to look at the edges here. Again, I'm going to line up short to short, medium to medium, and long length to long length. That goes with corresponding base edge, another base edge to the base edge, and so on. Just like we did with the similar figures, and it's like we read left to right, that's how I'm going to set this up. So I'm going to go 3, put that over 12, put the 1 over the 4 down here, and then put the 5 over the 20. I'd say the 5 is the height of the prism on the left, the 20 is the height of the prism on the right. Looking at them right away, they're obviously not similar, but just like anytime we're dealing with things that are supposed to be in proportion to each other, we want to make sure they are in simplest terms or lowest terms, so I'm going to reduce these. 3 over 12, that reduces to 1 over 4. 1 over 4, that's already the lowest, 1 over 4, and then 5 over 20, once again, I can reduce that to 1 over 4. So once again, I can see that all the base edges are proportional, so these two are two similar rectangular prisms there. Look at this next example. We have two square pyramids. And going left to right, how I set these up, again, one base edge and compare that to another base edge. Since these are square pyramids, I'm not going to worry about all the sides, but I'm just going to set up one. I go 14 over 7. That has to be proportional. I know this is not a side of a face of any sort. This is the height of one pyramid. I'm going to compare that to the height of the other one. So just like we've spent a lot of time throughout the course of the year on corresponding parts, with similar figures, corresponding parts have to be proportional. The same thing with 3D figures. Corresponding parts have to be proportional. So 14 over 7, I'm going to set that up and correspond that with the 10 over 5. And as you can both tell, both of these reduce to 2 over 1. So 2 over 1 is proportional to 2 over 1. Again, thinking about the parts of the two figures. The parts of one are going to be proportional to the parts of the other. So again, I would say these are similar. Lastly, looking at these, we have two cylinders here. Just as we've done, I have a height of one, a height of another, a radius of one, and a radius of another. So setting up to determine if these are proportional, I'm going to go the height of one, 13, over the height of the other, 10, and compare that with the height of one, 6, over the height of the other, 6. 13 over 10 does not reduce, but 6 over 6 does. I'm going to go 13 over 10 equals 1 over 1. There's no way I'm going to get 1 over 1 over 13 over 10. So I would say these two figures right here, these two cylinders, are not similar. So those are talking about similar figures. We're also going to talk about congruent solids. So similar solids, now congruent solids. We dealt with the word congruent for the majority of the year, and you guys all know what that means. I mean, the measurements are going to be congruent. So also with congruent solids, though, we have a couple other characteristics. You can see here 4 of them. Corresponding angles are going to be congruent. Corresponding edges are going to be congruent. The areas of the corresponding faces are equal. The volumes are equal. So an easier way to look at that with congruent solids is congruent solids are exactly the same shape with exactly the same size. So congruent solids are the same thing with these characteristics. So these next few examples, we're going to look at these and to determine if they are congruent, similar, or neither. Here's two rectangular prisms. So again, looking at the sides, we're going to do this a lot with the scale factors. Looking at the sides, I'm going to set up 5 over 5. They're kind of mirrored images of each other, so the 5 goes with the 5. The 4 goes with the 4. And then the 8 goes with the 8. Going through all of these, they all reduce to 1 over 1. So going back to one other characteristic, again, the ratio of the corresponding measurements is going to be 1 to 1. The ratio of all these measurements is 1 to 1, so I would say these are congruent solids. Number 2, I have a cylinder on the left and I have a cone on the right. I can tell that the radius of one is congruent to the radius of the other, the height of one is congruent to the height of the other, but these are going to be neither, and it's easy to see why, because they are not even the same shape. So rule number 1 is that they have to be the same shape in order to be similar or congruent. One last one, 2 cylinders this time. Again, I'm going to read right to left, or left to right I should say. So setting this up, again I have the height of one comparing that with the height of the other, so 21 over 7, comparing with the radius of one to the radius of another, 6 over 2. 21 over 7 reduces to 3 over 1. 6 over 2 also reduces to 3 over 1. Again, not 1 to 1, but 3 over 1, making these similar. Now we have 3 theorems that go along with similar solids as well. And I'm going to start, this is an important slide. So if the scale factor of the scale factor of 2 similar solids is A to B, then we're going to have 3 different theorems that go along. The first one is that the corresponding perimeter is going to be A to B. I'm going to elaborate on this a little bit. It's the perimeter, it's going to be the height, the slant height, it's going to be the height. So I'm going to lump all these together into parts. So whatever the scale factor is, if the scale factor is A to B, then any of the other parts, base edges, lateral edges, slant heights, etc., is also going to be A to B. But when we move on to the ratio of the areas, again, areas are always units squared. When we move on to ratios of the areas, notice what we do to the scale factor. It's going to be squared, A squared and B squared. When we move on to the ratio of the volumes, again, anytime we talked about volume, it's going to be units cubed. So now the ratio of the volumes is A cubed to B cubed. So let's get into a couple examples of these. First one is where we're going to look at 2 cylinders. It says they're similar, that's important. So I want to find the scale factor, the ratio of the heights, the ratio of the total areas, and the ratio of the volumes. So let's start with the scale factor. Again, reading left to right, my scale factor, I'm going to look at the radius of one, 3, over the radius of the other, 4. There's my scale factor of 3/4. Let's compare it back here to find the ratio of the height as this one's asking for. So we don't have the height here, but we know what the ratio is because, again, corresponding perimeter, if the scale factor is here, the perimeter, the slant height, the height, whatever else is a part, is going to be the same. So the ratio of my heights is also going to be 3/4. Ratio of the total areas. I do not know what the total areas is, but again, comparing it to what our theorem says, we square A, we square B, we get that from the ratio of the scale factors. So the scale factor here is 3/4, so I'm going to square 3 and get 9. I'm going to square 4 and get 16. The ratio of the areas is 9 over 16. One last time, the ratio of the volume, comparing back here, we cube A and we cube B. And A and B is the scale factor. Back to our example, A is 3, B is 4, so to cube that I get 27, that's 3 cubed, over 64, which is 4 cubed for the ratio of the volumes. So there's, again, I do not know what the heights are, but I know the ratio is 3 to 4. I do not know what the total areas are, but I do know the ratio is 9 over 16. And I do not know what the volume is, but I do know that the ratio is 27 over 64. Another example, dealing with these rectangular solids, these rectangular prisms here. Ratio of the perimeters this time. And let's start by finding the scale factor. And going from left to right, the scale factor is going to end up being 7 over 5. And scale factor, that is the same as the parts now. Perimeters fall into that category of parts. So the perimeters, the ratio of the perimeters is also going to be 7 over 5. Let's move on to total area now. Again, to move from the scale factor or the parts to area, I need to both square A and square B. Square the top and square the bottom of the ratio to the scale factor. So 7 squared is 49. 5 squared is 25. I don't know what the actual area or total area of either one of these prisms are, but I know the ratio is going to be 49 over 25. One last example. This time I'm actually given the volume of the smaller prism. I'm given that it's 60 inches cubed. I want to find the volume of the larger prism. So let's look at the information that we know. We know that the scale factor, again this is the same figures from the previous slide, the scale factor is going to be 7 over 5. Whenever we're going to find a missing measurement, whether it be area, volume, or slant height, whatever it is, we have to be talking about the same thing. Going back to this slide right here, again, talking about volume compared to the scale factor is A to B. Volume, again, down here is where I cube A and cube B. So I'm going to set up a proportion here. Something's going to equal, again, I put the smaller prism is on bottom, so the volume of the small prism is 60. That's going to go on bottom. I'm going to put X on top. I have to figure out what goes on the other side of the equal sign, or my other ratio. I cannot put 7 over 5 because that's talking about the scale factor. I need to talk about the ratio of the volumes here because that's what the problem gives us is the volume. So I need to cube 7 on top. I need to cube 5 on bottom. 7 cubed is 343. Over 5 cubed is 125 equals X over 60. Again, I cannot stress enough that you have to be talking about the same units here. Here's my scale factor, the ratio A to B. I go to my volumes, which is A cubed to B cubed. There's my proportion. We can all set this up and solve now. Cross multiply. I get 125X equals 343 times 60 is 20,580. Go ahead and give me a decimal for this. So I'm going to get X equals 164.64. Again, we're talking about inches cubed here. So this time we actually know what the volume is of the bigger one is 164 inches cubed. That wraps up the lesson, and the test will be on this coming Thursday.